Welcome to a lesson on conic sections in polar coordinates. In this video we'll look at the eccentricity of a conic. We'll look at how we can write the equation of a conic section in polar coordinates or polar form, and then look at how we can sketch its graph, and then we'll kind of do the reverse. If you're given a graph, how do we write the equation for that conic section? So when we look at conics in polar form, there's a few things that we need to look at first. With a conic section is that we have something called an eccentricity, which we'll represent with just the letter E. And this is different than the normal Euler's constant that we think about, that you probably would have saw like with exponential functions. It's just E for eccentricity here, so it's something a little different. We also have a directrix, which will just represent that as a D, and which we talked about, I think, the directrix when we talked about parabolas, but technically all the conics have directrix, a directrix, so we'll kind of look at that in a little bit more detail. So we have an eccentricity, we have a directrix, and then one thing that has to be true in all of these situations is that we have a focus at the origin. So if you remember, parabolas only have one focus point, but ellipses and hyperbolas have two foci. So either one of those focus points, either one of those foci could be at the origin. So we'll look at how the shape of the graph is determined by the focus being at the origin. So we have an eccentricity E, a directrix D, and then a focus at the origin. And so with that being the case, we can express a conic using one of two equations, and they're the same equation, it's just whether it's sine or whether it's cosine. So R equals the eccentricity times the directrix divided by the quantity 1 plus or minus the eccentricity times either the cosine or the sine of theta. So just as sort of a quick illustration here, I have a graph of an ellipse, and so notice for that ellipse, one of its foci, one of its focus points is at the origin. And if you remember when we talked about conics before, the graph will always curve around the focus point. So the focus is at the origin, the ellipse is curving around it towards the positive x-axis, and there actually is another focus point somewhere further down on the positive x-axis, maybe around 21 or 22 or so. And then we also have a directrix, so there's a sort of a green dotted line to the left of the origin. Again, remember when we talked about the directrix back with parabolas, remember that we talked about how the graph always curves away. So the graphs curve around the focus and away from the directrix. And again, in this case, we have an ellipse that is opening horizontally. And so if you notice, the directrix is a vertical line. All right, now I have a GeoGebra applet that we can take a look at here real quick, just to explore some things a little bit. On our graph here, again, we're in polar coordinates, so you can see the concentric circle radiuses. In this case, each radius is a distance of 5 further away from the origin. And then we have the spokes of our radial spokes coming out from the origin. Each line, I believe, is a pi over 12. So, pi over 4 would be a perfect 45-degree angle there. We also have a parabola in this case, so it's a parabola opening down. We have a focus. The focus of the parabola is at the origin, and since the parabola is opening down, remember that its directrix is going to be up above. In this case, the directrix is the line y equals 10. So the equation for this parabola is r equals 10 divided by 1 plus 1 times the sine of theta. And in this case, the eccentricity is 1 and the directrix is 10. Okay, so what I want us to look at here is if I start changing the value of the eccentricity, or if I start changing the value of the directrix, or if I change it from sine to cosine, how does that impact to the shape of the graph. So let's start with the directrix here. So right now, our directrix is at y equals 10, which is above, it's a horizontal line above the origin, and the graph opens down. So if that number gets smaller, it's just making my parabola, it's still a parabola, it still opens down, it's just changing and making it a smaller and narrower parabola. What would happen if it goes negative? Okay, so now if you notice, it switched, the graph is opening upwards, so it's still a parabola, it's just opening upwards, and we still have a horizontal directrix. Also notice what changed in my equation. When the directrix was positive, the denominator was 1 plus the sine of theta. When the directrix becomes negative, the denominator becomes 1 minus the sine of theta. Okay, the sign of the numerator didn't change, just that plus or minus in the denominator. Okay, so it's kind of backwards to the shape of the graph. If the directrix is positive, it's a plus in the equation, and the graph opens down. If the directrix is negative, that means the graph opens up, and it means it's a minus in the denominator of the equation. Because again, the graph has to curve away from the directrix, which means if the directrix is on the negative side, it has to curve up, so it goes away from the directrix. Okay, so we see again, just by changing the value of the directrix, it just changes whether the graph opens up or opens down. The other thing we might want to look at is what if we do a cosine instead? So let's switch this to cosine. So now we have a parabola opening to the left. And so our equation is 10, r equals 10 divided by 1 plus 1 cosine of theta. And again, our directrix is positive. Notice it's now a vertical line. So when we had sine, the directrix was a horizontal line, so it's horizontal. When we go to cosine, it becomes a vertical line, and it's x equals 10 in this case. When it was horizontal, it was y equals 10. So with cosine, you have x equals 10, and since that's positive, the graph has to open around the focus to the left. So it's going away from the directrix, around the focus. So our parabola opens to the left, and again, this would, hopefully you could probably figure this out, but if the directrix becomes smaller, the parabola gets smaller, and as the directrix becomes negative, it switches and changes the direction. And again, notice now I have a negative directrix, x equals a negative 3.5. The graph of the parabola now opens to the right, so it kind of goes in the opposite direction, and the denominator of my fraction is 1 minus the cosine of theta. It's still 3.5 on the top, positive 3.5, but the negative, we have that subtraction in the denominator. Okay. All right. One other thing to look at here. We want to look at what happens if I change the eccentricity. And we haven't really talked about what that eccentricity is yet. We'll look at it here in a minute. But what happens if we change this eccentricity? So right now, let's go back to sine. So we have r equals 10 over 1 plus 1 sine of theta. So what happens if this eccentricity, let's say it gets bigger. So right now the eccentricity is 1, and it still looks like it's a parabola. And if we keep making it bigger and bigger, and oh, what just happened? Okay, so if I change this eccentricity, let's just stop at 2. Do I have a parabola anymore? No, because there's 2 curves. There's one curve, it kind of looked like the parabola did before, that's opening down around the origin, but there's a second curve that's sort of reflected and opening upwards. And so this is a hyperbola. The directrix is still at y equals 10 and still horizontal line. But we have the second part, the second curve of the hyperbola. If we look at our equation, r equals 20 over 1 plus 2 sine of theta. So just, again, some things to connect here with our graph. It's a sine of theta, which means our graph is opening up or down. It's plus. So what I looked at before is I said that plus, it's going to describe the part of the curve that curves around the origin. So because it's plus, it goes in the opposite direction. So the curve, the part of the hyperbola that goes around the origin will curve down. It just means the other half of the hyperbola curves up. So we have this vertical hyperbola. The 2 in front of the sine, that's just your eccentricity. The 1 in the denominator is always 1, at least for it to fit our formula. So where does this 20 come from? Well, the 20, again, is just the eccentricity times the directrix. Or maybe we'll be more specific, it's times the absolute value of the directrix. Because what happens if we change d and we make it, if we change our directrix and make it negative? So right now, directrix is positive. The first half of our hyperbola opens down because it has to curve around the focus. So what happens if we make it negative? Okay, so if the directrix is now negative, we're at a y equals negative 10 line. Well, again, it did kind of the opposite thing. The directrix is negative. It's below the origin. It's below the focus point, which means the part of the hyperbola that curves around the focus has to curve up because it has to curve around the focus and has to curve away from the directrix. Okay. Now again, the other half of the hyperbola also curves away from the directrix. And in fact, it will actually have another focus here, maybe about negative 25 or negative 27 or so, that it is curving around as well. It's just not the one at the origin. Everything I'm talking about here references the one at the origin. So again, if the directrix is negative, the primary, the first half of the hyperbola is going to open up. And again, in our denominator of our equation, we have 1 minus 2 sine of theta. So that minus reflects that we have a negative directrix. But the numerator is still a positive 20. So it's the eccentricity 2 times the 10 of the directrix. The negative, we don't have to worry about that. We'll just keep it as a absolute value, or always positive. Okay. So what happens if we go to cosine? If the directrix is negative, that means the graph opens to the right around the focus, and then that second half will open to the left. But that primary one that goes around the origin curves to the right. We have an x equals for our directrix, and then if we made the directrix positive, notice it just shifts the graph now to the right side. So if the directrix is an x equals 10 on the right side, then the first half of the hyperbola opens again around the origin, so it has to curve to the left, away from the directrix, and then the second half of the hyperbola will curve off to the right. And again, notice our equation changed from a 1 minus 2 sine to a 1 plus 2 cosine, or 1 minus 2 cosine of theta. It's now 1 plus 2 cosine of theta. All right, so we looked at what happens if the eccentricity is greater than 1. So anything that's greater than 1 will produce a hyperbola. If it's equal to 1, we get a parabola. So what happens if it's less than 1? Well, there's really only 3 options. So if it's less than 1, yep, you probably guessed it, we're going to have an ellipse. And sort of the structure of all this is pretty much the same. So if we have, let's say we set the eccentricity to 0.7 and we leave the directrix at a positive 10. Okay, our equation is r equals 7. So again, that 7 is the 0.7 eccentricity times the directrix value of 10. And then in the denominator, we have 1 plus, so it's plus because the directrix is positive, 1 plus 0.7, which is the eccentricity, times the sine of theta. So because this is sine, the graph is opening, or the ellipse is stretching vertically. Because the directrix is positive, or we have a plus in the denominator of our equation, that means the directrix is above the origin, it's above the focus, and so that means the part of the curve, the part of the ellipse curving around the focus has to curve downward. So we have an ellipse that's stretching down the y-axis. So what happens if we change and make it a negative 10? So again, as the directrix gets smaller, it's making the ellipse smaller and smaller. If the directrix becomes negative, it's now flipping it and making it positive. So if the directrix is negative, That means you have a horizontal line, again, on the negative, y equals a negative 5, which means the ellipse has to open up. It opens in the opposite direction. And so our equation is r equals 3.5, which is the 0.7 times 5. And then denominator, we have 1 minus 0.7 sine of theta. And again, because this is minus, that tells me the directrix is negative, and it tells me the graph opens upwards. And again, if we flip this to cosine, it does everything horizontally. So if the directrix is negative, that means we have a 1 minus 0.7 cosine of theta, which means the graph stretches to the right. Okay, so that's just kind of a quick summary of the different graphs. And we'll kind of list these out as we keep going forward. But just remember, how does the directrix affect the graph? It tells you whether it opens up or down, or left versus right. Whether it's sine or cosine tells you whether it's horizontal or vertical. And then the eccentricity tells you the type. So it's the eccentricity is the one that changes the type of the graph. So what is this eccentricity? So let's go back to an eccentricity of 1 and a directrix of a positive 10. So again, this is a parabola opening downward. If you remember with a parabola, we had our focus point. We talked about having a directrix before, and we could even locate the vertex. So with this example here, the vertex would be at the point as an xy coordinate, it would be the point 0, 5. Now, if you wanted to describe that in polar coordinates, it would be pi over 2. It would be 5 comma pi over 2. But we'll just, for now, it's at 0, 5 if we thought about it in rectangular coordinates. How far is it from the vertex of the parabola to the focus? What's a distance of 5? How far is it from the vertex of the parabola to the directrix? Also a distance of 5. So one of the nice things that you see with parabolas is that the distance from the vertex to the focus is the same as the distance from the vertex to the directrix. And it turns out, and we talked about this when we looked at parabolas before, that is always true. It doesn't matter which point you pick. If I picked any point on the parabola, the distance from that point to the focus is the same as the distance from that point to the directrix. And that is what we mean by the eccentricity. So let's look at the eccentricity here. So we just talked about, for the vertex, the distance from the vertex to the focus is a distance of 5, and the distance from the vertex to the directrix is also 5. If we look at the ratio of that, we get 1. And so it turns out that that's giving me the eccentricity. And so if we change points, so as this point moves around on the parabola, notice that the distance from that point to the vertex is changing, right? It's 27.61 now, not 5. And so is the distance from that point to the directrix. But notice these two distances are the same. So that means if I compute their ratio, it will always equal 1. Okay, so no matter which point I pick, and this doesn't work whether it's sine or cosine. If we tried cosine, it's still going to be the same. Okay, these distances are always the same, and it doesn't matter whether it opens up or whether it opens in a different direction, whether it opens down or left and right. All this is always true. Okay, so it's a nice little something that we can see here. So what happens if we're talking about eccentricity, but it's not a parabola? Okay, so let's look at a hyperbola. So let's bump this up to 2 here. So for a hyperbola, we can still want to compare the distance from any point on the hyperbola to the origin and to the focus point compared to the distance from that point to the directrix. And so it's kind of hard to see here. Let me move it. But what we're going to see is these distances are not the same. Okay? If I compute the ratio of the distance to the focus point divided by the distance to the directrix. So this is the distance to the focus divided by the distance to the directrix. In this case, it's 2. So that means it's twice as far to the focus compared to just the distance to the directrixes. In this case, it's a distance of, it's double that. And it doesn't matter which part of the hyperbola I'm on, if I'm on the bottom half or the top half, right? It still works, okay? The distance to the focus divided by the distance to the directrix is still 2. And lo and behold, that 2 is the eccentricity. Okay, same thing would work if we did an ellipse. So let's go down to like 0.5. Okay, so any point on the ellipse, if we computed the distance from that point to the focus, it is exactly half of the distance from the point to the directrix. And again, that's all the way around the ellipse. And it doesn't matter whether it's a horizontal or a vertical ellipse. That distance is always a half. Okay? So again, we'll kind of spell that out here in a second, but I just want you to see visually what's happening, graphically what's happening when we talk about an eccentricity. So let's go ahead and summarize kind of what we're finding here. Okay, so when we talk about eccentricity, we are defining the eccentricity as the ratio of 2 lengths. It's E is the distance from any point to the focus divided by the distance from the same point to the directrix. So when we talk about eccentricity, we're talking about the ratio of these 2 distances. Okay, and then once we looked at that, what we observed is that we will have a parabola if the eccentricity is 1. Those distances are always the same. It will be an ellipse if the eccentricity is less than 1. In which, like for example, the example we looked at, the distance to the focus was half the distance to the directrix. And if we looked at if the eccentricity was greater than 1, then we had a hyperbola. So in the example that we looked at, the distance to the focus was twice the distance to the directrix. Okay, so the eccentricity is the ratio of the 2 sides or the 2 lengths, and then we can determine which type of graph we have, what type of conic we have based off of the eccentricity. It's either less than 1, equal to 1, or greater than 1. Well, what about the directrix? So just a couple things to think about here. The directrix is going to be perpendicular to your conic. So for parabolas, we had an axis of symmetry. It's sort of the line that cuts right down the middle. For ellipses, we have a major axis. And so the major axis was the line that passed through the center, through both foci, and then to the longest vertices, the vertices furthest apart from each other. So that's the major axis. Very similar for hyperbolas, we had the transverse axis, which passes through the center, through the vertices, through the foci. On the far ends. Okay, so the directrix will always be perpendicular to those. So if you have a horizontal directrix, you will have a vertical conic, and vice versa. If you have a vertical directrix, you will have a horizontal conic. So for a horizontal line, we'll have y equals, and it could be a positive or negative, whether it opens up or down. And it will be, if it's a vertical directrix, it will be x equals plus or minus d. Okay, so how do we put that together to understand the shape of the graph? So we know the graph will be vertical if the sign is, if we have sine in our equation, and it will be a horizontal graph if we have cosine in the equation. We know it is perpendicular to the directrix. We just talked about that. We know it will open in the opposite direction of the sign in the denominator. Okay, so if you have a plus in the denominator, so if it's a plus in the denominator, that means your directrix is positive, and so your graph, your conic, will either open left or down. If you had a minus in the denominator, then that means you have a negative directrix, which means the graph opens up or to the right. And then again, just in general, the graph will always curve away from the directrix. It will curve around the origin. So away from the directrix and around the origin. And for the most part, the graph should never cross the directrix. Okay. So if you have you can't have a parabola that's opening horizontally and a horizontal directrix, because they're going to cross at some point. They have to be perpendicular to each other. Okay, so let's just look through some examples here. Let's just start with some given information and see if we can write out what the equation would be, maybe sketch a graph, and then identify like the eccentricity and stuff. So for this first example, we have a parabola, and we're given the directrix equation is y equals 2. Okay, so for me, I personally like to draw, to get it to draw a graph. Like I'm just very visual. I like to see what I'm looking at. So I have a parabola, and I know the directrix is y equals 2. So y equals 2 is a horizontal line. I have a horizontal line at y equals 2, and remember the graph has to curve away from the directrix around the focus. So because the horizontal line is at a positive 2, I know the graph has to open down. And remember the directrix is perpendicular to the graph. So a horizontal line means I have a perpendicular parabola. So it has to open down around the focus, around the origin. Okay. So what else can we tell about this parabola? Particularly if we want to try and write the equation. So because it's a parabola, what do we know about the eccentricity? Well, because it's a parabola, I know the eccentricity is 1. So I know E is equal to 1 in my equation. I also know the value for the directrix D is equal to 2. Now, whether it's plus or minus, D is always going to be a positive value, so it's just D is always a positive 2 in this case. Because it opens down, okay, because it opens down, I know the denominator of my equation is going to be a plus, because it's opposite, and the sign in your denominator matches the sign of your directrix, and it's a positive 2. And because it's vertical, I know that I'm going to have sine in my equation. So again, if we remember our equation, it's R equals the eccentricity times the directrix divided by 1. And again, in this case, it's going to be 1 plus the eccentricity times the sine of theta. So we just need to put stuff in. We put a 1 for E in the numerator and in the denominator, and then D is a 2. And so our final result is R equals 2 divided by 1 plus the sine of theta. All right, let's try another one. We're told we have an ellipse with a directrix at y equals -4, and the eccentricity is a half. And again, I like to draw a graph here. So it's going to be an ellipse, and the directrix is a -4. So let's draw that -4 line. So y equals -4 is a horizontal line, and so it's going to be down here below the x-axis. So because the directrix is below the x-axis, the conic has to open away from that. So it's going to open up. It can't open left and right, because if it did, it would cross. So it has to open up. It curves away from the directrix. So it looks like my ellipse is stretching vertically, mostly into the top half of the xy plane. So that's sort of what our graph would look like. So what else do we know? And again, we want to be able to identify the same things. So it's an ellipse, and we were already told the eccentricity is a half. The directrix, our equation is y equals a -4. So just ignore the negative, pull the 4 out. So we know D is equal to 4. And then because the ellipse stretches vertically, I know it has to be sine, and because it's going up, it has to be negative. And remember, the sign of your directrix here will match whether it's a plus or minus here. So because this is a -4, this is a negative. So it's going to be a minus in my denominator. All right, so what's my equation look like? Again, in general, R equals the eccentricity times the directrix value divided by, in this case, it's going to be 1 minus, because again, we have a minus directrix, 1 minus E times the sine of theta. And again, it's sine because the ellipse is opening vertically. Just plug your values in. E is a half in the numerator and the denominator. D is 4. So a half times 4 gives us R equals 2 divided by 1 minus 1/2 sine of theta. All right, let's look at another one like this. So this time we have a hyperbola. Its directrix is x equals -3, and that's a little different. So we have an x equals equation. and the eccentricity is 4/3. Notice the eccentricity is greater than 1, which is that fits into some of the criteria that we looked at earlier. So again, let's draw a picture. So the directrix x equals -3, that is a vertical line because it's x equals, and it's a -3, so it's going to be a vertical line to the left of the origin. So x equals -3, it's 3 units to the left, it's a vertical line. And remember, the primary curve of the hyperbola has to curve away from that line and around the focus, around the origin. So that means if the vertical line is to the left of the origin, that means this first part of the graph has to open to the right, because it goes in the opposite direction. So we have 1/2 of the hyperbola opening around the origin to the right, which means somewhere out here over to the left we have the other half of the hyperbola. Now we can find it more specifically if we want to, but right now we're just getting a quick sketch so we know what we're talking about here. All right, let's go through the same process. Because it's a hyperbola, we're already given the eccentricity as 4/3. Because the directrix was x equals a -3, we just drop the negative, so we know d is equal to 3. Because it is x equals, we know the graph is, or the equation is going to be cosine, and because it's a -3, I know it's going to be a minus cosine in the denominator. All right, so putting our equation together, r equals eccentricity times the directrix over 1 minus the eccentricity times the cosine of theta. And again, it's minus because the directrix is negative, and it's cosine because it's an x equals directrix. The eccentricity is 4/3. And the directrix is 3, and if we multiply the 4/3 and the 3, we'll get the equation r equals 4 divided by 1 minus 4/3 cosine of theta. All right, let's look at one more along this kind of route here. Let's just change it up a little bit. We have an ellipse with an eccentricity of 0.4 and a vertex of 2, 0. So in this example, we're not given the directrix. So we're given slightly different information here. We're still given the eccentricity, and it's less than 1, which matches our criteria. But we're given the vertex instead. So what's not stated here, but is assumed, is we still have the focus at the origin. Okay, so let's put together what we have and see what the graph will look like. So I know I have a focus at the origin, and I know I have a vertex at 2, 0. So the graph has to curve, it has to pass through this vertex, and it has to curve around the focus. Okay, and the vertex that we're talking about is I guess sort of the vertex closest to the focus. So that tells me that the distance from the focus to the vertex is a distance of 2. And because this is the closest vertex, it has to curve away from, it has to curve around the focus, right? So it has to curve that direction. And so that would tell me that the directrix has to be to the right of the vertex. Okay, so we have an ellipse that opens to the left or stretches to the left, which means it's horizontal. And because it's horizontal, we have to have a vertical directrix. And we don't know what the value for the directrix is. We're going to have to figure that out. But we do know it's going to be a vertical directrix because we have a horizontal ellipse. So how do we go about finding this directrix? Well, remember that eccentricity was defined to be the distance to the focus divided by the distance to the directrix. And we know that the eccentricity is 0.4, which if you want, you could write 0.4 as the fraction 2/5, or you could write it as 4/10, it doesn't matter. So we know the eccentricity is 2/5, and we know the distance to the focus point. So from the vertex, and it doesn't have to be the vertex, it can be any point on this ellipse, but in this case, we're given where the vertex is at. So I know the distance from this point to the focus is a distance of 2, because that's where we were told the vertex was at. And so it sets up sort of this little proportion. We know the eccentricity is 2/5 or 0.4. We know the distance to the focus is 2. And so we want to solve for the distance of the directrix. This one's pretty easy to solve, but if you don't remember how to, if you can't just do it visually, then just remember you can cross multiply and divide. So diagonally 2 times d has to equal 2 times the 5. So you get 2d is equal to 10, you divide the 2 over and you get 5. Okay, which should make sense. If 2/5 is equal to 2 over d, then the d has to be 5. But anyway, so we just found that the value for the directrix. Okay, so let's kind of list through the sort of the criteria for this graph. We know it's an ellipse, and we know it's an ellipse because the eccentricity was 4/10 or 2/5, which is less than 1. The directrix, we know it has to be x equals because it's a horizontal ellipse, which means it's a vertical directrix. And it's positive, it's on the positive side, it's on the right side of the ellipse because the ellipse opens to the left. So we have x equals 5, which means the directrix is 5. We know it opens to the left because it has to pass through the vertex and go around the focus, so it has to go to the left. Because it opens to the left, that means the directrix is positive, which means we're going to have a plus in the cosine, and we're going to have a plus cosine in the denominator of our equation. So again, let's put all this together here. We're going to have r equals the eccentricity, which is 2/5 times 5, and then divided by 1 plus the eccentricity again times the cosine of theta. So we get r equals 2 divided by the quantity 1 plus 2/5 cosine of theta. So that was a little harder because we weren't given the directrix, but we can still figure it out just by using our definition for what the eccentricity actually represents. Okay, let's flip this around a little bit. Let's look at some examples where we're given the equation and we want to go ahead and sketch its graph. So we want to, if we're given the equation, the things that we need to be able to do with the equation, we need to sketch its graph, but we also need to determine what its eccentricity and directrix are, and from that, then we can figure out what type of conic we're looking at. So in this first example, we have r equals 6 divided by 1 plus cosine of theta. So remember our generic equation, the numerator, which in this case is a 6, our generic formula says that 6 has to equal the eccentricity times the directrix. So we know whatever the E and the D are, when you multiply eccentricity and directrix, you have to get 6. In the denominator, we have 1 plus cosine of theta, and we know in general there's an E right in front of the cosine. So it's 1 plus E cosine of theta. So since there's no number in front of the cosine, it's assumed to be a 1. So that tells me right off the bat that the eccentricity is 1. And if the eccentricity is 1, I know it has to be a parabola. Okay, so right now, just a real quick glance at our equation. I know the eccentricity, and I know that the type of conic, eccentricity is 1, it has to be a parabola. Okay, other things I can figure out from here, because it's a plus in the denominator, a plus cosine, I know the graph has to open to the left. Okay, so what about finding the directrix? Well, again, remember the numerator of our formula, the E times D, has to equal the 6. So, and we know that the eccentricity is already a 1. So that means that the directrix, the value of D, has to equal 6. And if we apply the fact that we know we have a parabola that opens to the left, that means the directrix has to be to the right. And because it's opening to the left, that's horizontal, I have to have a vertical directrix. So it's going to be x equals a positive 6. Okay. So how do we go about graphing it? Well, we could just do a quick sketch just from the information that we have, but I want to show us how we can actually plot the points for this. So what I want us to do is create like a little, you probably did an XY table when you were in algebra or something like that, when you're first learning how to graph. You can do the same thing, but using theta as your independent variable and then r as your dependent variable. And so there's 4 angles that I want us to pick for theta. And they're just the 4 quadrants, your 4 axes. So 0 is the positive x, pi over 2 is the positive y, pi is the negative x-axis, and 3 pi over 2 is the negative y direction. So I want to plug those 4 numbers into our formula. So if we take the 0 and we plug it into the theta, so we have 6 over 1 plus the cosine of 0. Well, the cosine of 0 is a 1. So that means we have 6 divided by 1 plus 1, which is 6 divided by 2, so 3. So in the direction of a 0 angle, we're going to go 3 units. So that's 3 units in the positive x direction. If we plug pi over 2 in for theta, cosine of pi over 2 is 0. So we get 6 over 1 plus 0, which is just a 6. So that's 6 units in the positive y direction. I'm going to come back to pi here in a second. If we jump to 3 pi over 2, well, cosine of 3 pi over 2 is again 0, so we're going to get 6. So what happens if you put pi in for theta? Well, the cosine of pi is a negative 1. And a positive 1 plus a negative 1 is a 0, and 6 divided by 0 doesn't exist. You can't divide by 0. So in this case, it's undefined. Now, that may seem kind of weird, but we'll see why it's that way if you remember that we have a parabola. So let's go ahead and plot our points and make sure everything matches up. So again, at an angle of 0, we have a distance of 3. At an angle of pi over 2, we have a distance of 6. At a distance of 3 pi over 2, we also have a 6. So this is actually 6 on the negative y direction. And then what happens if you go in the direction of pi? Remember, pi is the negative x-axis, but we have a parabola. What's the parabola never going to do? The parabola is going to continue opening forever. It's never going to come back down and touch the x-axis. So because it doesn't touch the x-axis, the function is not defined in the x direction. And that's why we got that undefined, does not exist value when we tried the pi, because the graph doesn't close, it doesn't touch the x-axis. So we have, based off the values that we had, I know that I have a parabola. Again, the eccentricity is 1. It opens to the left because I had a plus cosine. And if it opens to the left, we have to have a directrix on the right side, and it's a vertical line, which is x equals 6. All right, let's try another one. So we have r equals 6 divided by 3 minus 2 cosine of theta. Now, right off the bat, you should notice something different. In every example that we've done and in the formulas that we defined, this first number in the denominator has to be a 1. And in this example, it's not. We need to make it a 1. So to do that, we are going to take every number, every term in our function, and we're going to divide it by 3. So 6 divided by 3 is 2. 3 divided by 3 is a 1. That's why we divide by 3. And then 2 divided by 3 is 2/3. So I can rewrite this original function as 2 divided by 1 minus 2/3 cosine of theta. Now, if we match that up to our formula, again, right off the bat, we know we have an eccentricity of 2/3, because that's the number in front of cosine. So the eccentricity is 2/3, which that is less than 1, which tells me I have an ellipse. The other thing I can look at is because I have a minus cosine, that tells me the graph has to open to the right. Remember in the last example, we had a plus cosine, it opened left. So a minus cosine opens to the right. And then if we look at the numerator again, we know the eccentricity times the directrix has to equal 2. So the E times D has to equal 2. And we know the eccentricity is 2/3. So we have 2/3 D is equal to 2. If we were to multiply both sides by 3, and divide by 2, or if you divide both sides by a 2/3 fraction, you end up getting that d is equal to 3. Okay, so we know the value of the directrix is 3, and because the graph opens right, I know it has to be x equals a -3. It's negative because it's in the opposite direction, so right goes left, so it's -3, and it's x because it's a cosine, it's a graph opening to the right. All right, so let's try and go through creating this little table here. Again, we're using the same angles. Theta is 0, pi over 2, pi, and 3 pi over 2. So if we take 0, and I'm going to go back to the original equation just because it's a little easier, but if we take 0 and put it in theta, again, cosine of 0 is 1. So this fraction becomes 6 over 3 minus 2, and 6 over 3 minus 2 is just 6 over 1, which is 6. If we did pi over 2, well, cosine of pi over 2 is 0, so you have 6 over 3, which is 2. Cosine of pi is a -1, so if you have 3 minus 2 times a -1, that becomes 3 plus 2, and so that's going to leave us with 6/5, and I can't simplify that anymore. Or you could write it as 1 1/5 if you want, I guess. And then at 3 pi over 2, again, the cosine of 3 pi over 2 is 0, so we get 6 over 3 is 2. So remember these directions. This is x, y, -x, -y, and those are the distances I travel in each of those directions. So in the x direction, I have a distance of 6. In the y direction, I have a distance of 2. In the negative direction, I have a 6/5. And the negative y, I have a distance of 2. Now, I wrote them here as negatives. That's just more a rectangular location as opposed to a polar distance, but just so you kind of know where it's at. So the way once you connect those 4 dots, you're going to end up with an ellipse that's stretching longer to the right, which means the directrix is to the left, which makes the directrix a -3. It's a horizontal directrix, so we have an x equals. So again, that should match up with all the stuff that I talked about over on the first part of our problem. All right, let's do a couple more. We have r equals 10 divided by 1 plus 4 sine of theta. We have that 1 there already, so we don't need to do anything fancy. We can just start breaking this apart. So again, we know from our equation, the 10 has to equal the eccentricity and the directrix. And then the eccentricity is the number in front of sine. So in this case, the eccentricity is a 4. So E is equal to 4, and because that's bigger than 1, I have a hyperbola. I can also quickly just observe that it's a plus sign in the denominator, which it's now sine. We haven't done that for a while. But plus sign means the graph opens down. Right? Sine is vertical and it goes in the opposite direction, so plus sign goes down. What about the directrix? So I know, again, we already said that the eccentricity times the directrix has to equal the numerator 10, and we know already that the eccentricity is 4. So 4d is equal to 10, which means 10 is 10/4 or 5/2. Okay, so we know the value of the directrix. Because the graph opens down, I know it has to be a positive value, and because it opens down, I have to have a horizontal, a perpendicular. It has to be perpendicular down. It has to be a horizontal directrix. So I get y equals 5/2, or y equals 2.5. Let's go ahead and set up a table again. Again, we're going to do 0, pi over 2, pi, and 3 pi over 2, always the same 4 values. And again, I'm going to use the original equation. So if I plug 0 in for sine, well, sine of 0 is 0. So we get 10 over 1 plus 0, which is just 10. If we plug pi over 2 in for the sine of pi over 2 is a 1. And so we're going to have 10 over 1 plus 4, which is 10 over 5, which is 2. If we try pi, so again, plugging in pi, for sine of pi is 0. We're going to get 10 again, just like we did with the theta is equal to 0. Last one, this is going to be the weird one, since it's a hyperbola. If we plug in 3 pi over 2, 3 pi over 2 makes sine a -1. So 1 plus 4 times a -1 becomes a 1 minus 4. So we have 10 divided by a 1 minus 4, which becomes a negative 10 over 3, or 10 over a negative 3, doesn't matter. Okay. So what does that mean? So again, remember we have positive, the x direction, the y direction, the negative x direction, and the negative y direction. So when we go to plot this, okay, in the x direction we go a distance of 10. So it's 10 units to the right. In the y direction we go a distance of 2. So from the origin you go up 2 units. In the pi direction, which is the negative x-axis, we go a distance of 10. So we have this negative 10 on the left side. So there's the symmetry. So these 3 points define the first curve in our hyperbola. What about the fourth point? So 3 pi over 2, remember that is the negative the negative y-axis. And if we look in that direction, our radius is a negative 10/3. So remember, what happens when you're plotting a polar coordinate and your radius is negative? It meant that we flipped the point across the origin, a complete diagonal or completely directly across the origin, 180 degrees across. So normally I would plot 3 pi over 2 and 10/3 down the y-axis, but because it's a negative 10/3, it's actually going to flip up above the y-axis. So it's up on the positive y-axis. This point at 10/3 is the vertex for the second half of the hyperbola. So the second half of the hyperbola is going to pass through 10/3, which is bigger than 2, by the way, and it's going to open up sort of as a mirror image. So since the original part of the hyperbola, the original curve, original half here opened down, the second half has to open up. Okay, and again, this one's kind of a weird one, just like the parabola was, because it's a negative radius, it flipped across the origin up to the top. Okay, so let's just check to make sure that it matches up. We said the eccentricity was 4, which meant it had to be a hyperbola. Because it was a plus sign, it had to open down. So that's this first one here, it's opening down. And the directrix is a horizontal line, y equals 5/2, and that would all match up. Remember, 5/2 is bigger than 2, but it's smaller than 10/3. So it will fit in between there. All right, let's do one more and then we'll be done. So we have r equals 2 divided by 5 minus 5 cosine of theta. Again, first thing you should observe right here is you do not have that 1 to be in things with. So the denominator is not a 1 minus, it's 5. So how do I make it a 1? Divide by whatever's there. So I need to divide all 3 terms in this fraction by 5. So 2 divided by 5 is 2/5. 5 divided by 5 is 1. And then a minus 5 divided by another 5 is a 1 again. So I can rewrite the original function, the original formula, as 2/5 divided by 1 minus a cosine of theta. So again, the eccentricity is the number in front of the cosine, which in this case it's a 1. So I know the eccentricity is 1, which tells me I have a parabola. It's again a minus cosine, which means the graph opens to the right. To find the directrix, I know the eccentricity times the directrix has to equal 2/5, and I know the eccentricity is a 1, which means the directrix is also 2/5. Because remember, for parabolas, remember those distances are the same. And since the graph opens to the right, I know the directrix has to be to the left, so it's x equals a negative 2/5. Let's go ahead and create our table. So again, 0, pi over 2, pi, and 3 pi over 2. If I plug 0, we'll go back to the original equation. If I plug 0 into cosine, that's a 1. So 5 minus 5 times a 1 is just 0. So I'm taking 2 divided by 0, which is undefined. If I plug pi over 2 in for cosine of pi over 2 is a 0, so the minus 5 is just gone. So it's 2/5. Same thing is going to happen if you do 3 pi over 2, because cosine of 3 pi over 2 is 0, which makes the minus 5 a 0, so you're left with 2 over 5, so 2/5. So if we did pi, so cosine of pi is a negative 1. So if you have 5 minus 5 times the negative 1, that turns out to be 5 plus 5, double negative there. So 5 plus 5 is 10, and so we get 2/5, or sorry, 2/10, which simplifies down to 1/5. All right, so let's plot our values. So we know in the 0 direction, which is the positive x-axis, there's no point. In the positive y direction, we're going to have a point that's 2/5 away from the origin. In the negative x coordinate, negative x direction, we're going to have a point that's 1/5 away. And in the negative y direction, we're going to have a point 2/5 unit away. So if we plot those out, again, in the positive x direction, there's no point because it was undefined. That's a 0 angle. When we go pi over 2, that's your 90 degrees. We have a point that's 2/5 unit away. When we go pi, remember that's the negative x-axis, we have a point at a 1/5. And when we go 3 pi over 2, that's the negative y-axis, we have another 2/5 unit away. So from those 3 points, if we just connected those 3 points, we know the parabola has to open to the right. And if it opens to the right, that means our directrix is over here on the left side, which means it has to be an x equals a negative 2/5. And again, that matches up all the stuff that we figured out at the beginning of the problem.